So, good morning. So, we'll start the session of the second day. And the first speaker is Professor Seunghwan Kim from Asia Pacific Center for Theoretical Physics, APCTP. And he'll talk about a few problems of functional self-realization in brain.
Okay, thank you for the invitation. Well, I tell you how to read this. It's called APC, then TP. It's much easier to remember. Right. So this work is done in collaboration with Dr. Cho and Lee, and Dr. Shin is here with a poster over there. Well, just let me briefly mention about APCTP. So it's founded by founding President Seunghwan 10 years ago. So we have a second president, Professor Laughlin. I do not have a picture yet, but the third president is Professor Peter Fulden, who is the director, has been director of Max Planck Institute of Physics of Complex Systems in Dresden for the last 10 years. So now it's located in Pohang at the campus of POSTEC. That's the main institution I'm associated with in Korea. Now 12 member countries. Now we are cooperating with a number of Japanese research institutes, including Yukawa Institute of Theoretical Physics. So I'm very honored to be invited here. And we are working on international cooperation, active activities, and the training of young scientists. So we have a budget of $3 million a year, about 40 international activities, and about 2,000 meetings. So if you're interested, you are welcome to continue to visit the center. Outline of this talk will be, so I'll be first talking about functional self-organization in cultural development. And this will be main topics of this talk. But at the end, I'll briefly mention this functional network formation in the SDP neural network model. In fact, a poster will be given by Dr. Shin over there, so I did not elaborate. So I just mentioned briefly about the functional pathways study we are doing in EEGs. Well, some of you already very well know some basic facts of the brain, but let me go briefly about this. So we all know now neuron is the fundamental building block of the brain, which is a very slow processor, but it's capable of doing highly nonlinear and complex responses. Brain itself is a massively interconnected network of these neurons with these many neurons, and many more synapses, which form a certain kind of circuits and structures in terms of layers, the physical loops, and so it can be considered as a network of networks. It's fascinating because it's capable of doing highly complex and correct responses, which allows us to do, so sensory information processing, the way I do it now, movement coordination and learning, memory and cognition, all kinds of wonderful things is associated with. But these are, in a way, correlated to so-called activity-dependent neuroplasticity. This circuit is not fixed. It's changing in time, depending on the activity. So this change of hardware also affects the activity. So there's an ever-present question of the connection between structure and functions. And so this is naturally related to this question of what is the role of the functional organization in the brain. Well, this is basic facts on neuron. Neuron is a somewhat complex structure. It's capable of computing by dynamics of membrane potentials. So depending on the stimulus, it's capable of firing so-called action potentials of particular form. And so it's basically electric signals. Where it's based on complex electron biochemical process in the cell. I won't go in details, but the problem of this ion conductances through these membranes create currents, so this is associated with the nonlinear voltage gating. But these are all related to some physiological experiments some time ago on, say, for example, this seminal experiments on giant axon speed by Huxley, in a way mapped this problem of neural signal generation and conduction into a kind of circuit, equivalent circuit. So because electronic circuits can be written down in terms of, say, differential equations by Kirchhoff's law. So you can write down equation of motion in terms of ordinary differential equations. In this case, it's four-dimensional ordinary differential equation. So then you can solve these ordinary differential equations numerically, sometimes analytically, if it's simple one, and to understand time evolution of this membrane potential and creation of nervous signals. Not only just this Huxley neuron, its variations based on the conductions has been basis for creating more complex and realistic models of many nervous systems. These neurons interconnect with each other, so when in the connection, there's connection geometry, it's globally connected, local sparse. Also, the interactions through the synapses, which couples activity of neuron to another in various forms. Also, the external stimulus or noise are playing very important roles in creating models of neural networks. So this somehow maps the problem into kind of dynamic system models for nervous dynamics. Now, if you look at the brain, it's not a single structure. It's a kind of a hierarchy of different structures and different spatial scales, from nanometers to the beta scale, from ion channels to this central nervous system. So, but how to model is a complex issue. It's not just a single question, but depending on what you are interested, you can come up with different sorts of models, or which is related to different research areas. And so you can focus on these nano devices for biophysical models, or you can try to understand dynamics of neurons and networks through these nonlinear dynamic models. Or you can work on more, simplified but immensely connected neural network models. Also, you can work on higher level, more coarse-grained cortical models for development. That's something I'm going to focus for today. But also, you can try to get measured biosignals, so EEGs or MEGs from brain. Try to understand the pathways using time series analysis. But it's different kind of areas of knowledge, expertise necessary. Dynamics, biophysics, complex system theory, physical physics, or neural network theory, or linear time series analysis. So what our focus is now is this functional self-organization in visual maps. So here is visual stimulus. So you are getting visual stimulus now through this screen, and then this optical information is transformed into say electric information at the retina by neurons, and it's transported back to the back end of your brain, the cortex area called the primary visual cortex. It's where the information is processed. Well, depending on stimulus, neurons respond differently. So, for example, these stimulus have different orientation. So, stimulus of different orientation, horizontal or vertical. And for these cortical neurons on this so-called primary visual cortex area, and this neuron responds differently. Some respond vigorously, some peasant. So they show kind of orientation preference. they like some stimuli. This can be more, carefully and studied by using the optical imaging techniques. So basically, what the experiments do is they do to this poor monkey. They shine a laser while this is exposed to this visual stimulus, of in this case vertical line. Then try to record some optical information through the camera. So the basis is this neural activity is correlated with the hemodynamics. And then this information is transferred back to the computer to reconstruct some patterns. So what you do is basically scanning through this cortex, especially this visual cortex area. Well, the structure of the cortex can be interpreted in terms of so-called pseudo two dimension, because this is the section of the cortex, the surface area of the brain, and then here's the deeply penetrating neural structures, and these neural structures is in a way grouped into so-called columns. So this columnar structure kind of forms the basis of some functional neural coding. So in this case of orientation preference neurons, a group of neurons forming a column, they are arranged in a very well organized way. So here, your vertical columns, they are organized in a somewhat continuous way. So we can take advantage of these cortical structures in neural modeling or development. So this is basically what is observed experimentally. In this case, the case of tree shrew. This is data 10 years old. And this is a somewhat beautiful complex pattern. Actually, the cortex area, which is crumpled, is stretched to give you a two-dimensional view. And how you see this picture? Well, I mean, here's the stimulus. So horizontal stimulus is color-coded by red, and this vertical stimulus is color-coded by this sky blue. So each area with the red colors corresponds to neurons which like this particular stimuli. So you have this map of neurons with the orientational preference in two dimensions, or neurons or neuronal columns. And then, so this map is non-existent for, say, young tissue when it's born. So after a couple of weeks, then this map starts to form. So from here, you can note some patterns. For example, I mean, in some of areas where different colors cross, or here, so around this point, you can find all the colors, the old orientation. Right at this point, orientation preference disappears. So this is a singularity, which is called pinwheel. So depending on the orientation of these colors, then you can have pinwheels or anti-pinwheels. Also, in some other parts, especially near the boundaries, you see a parallel, stripes. So here's called linear zones with the periodic patterns. These are combined to form this magnetical view of this pattern, and to form a complex picture with the linear zones and pinwheels and anti-pinwheels. So, while there are a number of, say, physiological facts about the properties of these pinwheels, how they disappear, things like that, and so which have to be tested in a way with models. Well, in visual cortex, there are different layers of maps. It's not just the orientation preference map. There is so-called ocular dominance map. This is in a way simpler because ocular dominance is related to whether you like stimulus from the left eye or right eye. So we have two eyes. So depending on whether you like the stimulus from left or right, we can color them differently. So this is one of the experimental observed maps. So how are these two maps, overlay with each other? Well, exact geometry is not known, it's more functional. But schematically, this is the way you build. You have these functional columns, and you have this orientation preference map. Also, we have embedded this ocular dominance map. They interact with each other in some way, anyway, compete with each other. So what I'm showing now are actually experimental facts, because in different class of mammals, in scale like monkey and cat and tissue, they show different visual maps. For example, in the case of this monkey, this is ocular dominance map. So we have left and the right eye, so you have two colors, black and white. And it shows stripe pattern. So you also here see strong appearance of ocular dominance maps. In this case of cat, this pattern is pretty different. So it's more like island patterns with blobs. In the case of tissue, we do not see ocular dominance map. This is very big, or no maps. But instead, this orientation preference map is very, very strong here. So this is what I showed you before. So you have a quite different class of this ocular dominance map and the correlated orientation preference maps. Question is, why do they show these different behaviors? Can you explain them in terms of models? The approach I'm doing is very simple in a way, because we believe and we're convinced that this simple model is capable of explaining these different types. Also, it's certainly incorporates only the kind of simple symmetry and simple interactions between functional columns. This is consistent with other types of neural development models, which has been studied before. Basically, we look at this problem as a two-dimensional layer of visual columns. And at each side, you have a so-called functional column with a particular parameter called angles, phase angles, which denote orientational preference. So this should change in time under some evolution equation I specified here. And this is basically coarse grained picture at the functional column level. But certainly it will be interesting to reconstruct this model with a number of neurons forming functional column. That's another effort. Basically, this phase angle of the column evolves in time while depending on some Hamiltonian. And so it's time evolution is a gradient of some Hamiltonian. Basically, it's related to whether input from the so-called LGN, which is a pathway between this retina to the primary visual cortex. So it's external stimuli or it's an interaction with the neighboring columns. Basically, this interaction depends on the differences in their angles. So it's periodic function with some interaction function. This interaction function is so-called distance-dependent. When it's close, in short range, it's exactly. And it's far away, there's long range inhibitory. This kind of typical type of interaction, which are often used in neural models, so-called Mexican head type. Well, here's one functional form, so where this K and sigma specifies the rate, strength and the range of these inhibitory interactions, which are important, say, control parameters describing bifurcation later. Well, this has a very strong analogy to so-called problem model of spin Hamiltonian often studied in magnetism. That's one motivation for this study. Because this orientation preference can be with phase angles in terms of this kind of sort of spins. This spin has all orientation. So in this case, these spin interactions have the form of XY, so-called XY model in statistical physics. In the case of ocular dominance, then this spin can take either plus or minus one depending on left and right. Then it has character of Eisenman. So So this kind of analogy is strongly used in understanding what's happening in this map formation. So XY model-like behavior is connected to the orientation preference map, and IT model-like behavior is connected to the ocular dominance map. So we can solve this equation numerically to see time evolution of vision map over time. So depending on the, say, some of the parameters, in this case, arbitrary strengths, that you can either have no map, so-called homogeneous state, or you can have a map. While in the context of bound system, it's called spin wave state. So this system is capable of producing fairly complex maps, which is so similar to what is observed. In fact, this orientation preference ocular dominance maps are strongly correlated. So experimentally, you can have two maps. You can compare the contours, the isocontours of these two maps, and they have a strong correlation. So, for example, so in order to understand that, we have formed a kind of combined model of XY and ID with the different interaction strengths for orientation preference and ocular dominance. So we can do the simulation under the condition that this so-called input, synaptic input, have to be in a way normalized, so that this orientation preference map and ocular dominance map, they have to compete with each other. In this way, this OP and OD maps are correlated. Under this condition, you can do the simulation. This is the result of the simulations. And basically, what it shows is that, and these color maps are orientation preference maps, and this black and black lines are contour curves of ocular dominance map. So it is at the center of this ocular dominance map, here blobs in ocular dominance map, and so you can find a so-called pinhole singularity. So pinhole singularity is always identified with the center of this ocular dominance blobs. So, which is better shown here in this mounted view of these ice contours. So these are in fact, these predictions are consistent with what has been experimentally observed. So in this sense, we are trying to have very strong analogy with phenomena of vortices in mountaism. So for this combined model, we try to understand the bifurcations. And there's two types of bifurcations. One bifurcation is over the elliptic strength, so which creates spin waves, so-called orientation preference map. That's what I showed you before in previous slide. Another bifurcation, which is not quite trivial, is bifurcation over this ratio between two interactions, whether orientation preference is stronger or ocular dominance is stronger. Okay? So this parameter we call anisotropy, because that's sort of related to an anisotropic Heisenberg model in the context of statistical physics. But this is, in the context of mountain theory, it's called creation of so-called out-of-plane vortices, not in-plane, out-of-plane, called scalar vortices. So now we realize this creation of this scalar vortices is correlated with creation of ocular dominance map, which is shown in these figures. 4 different quadrants, these two bifurcation lines, and you have this orientation preference map and this ocular dominance map. So you see a creation of ocular dominance here, also you see creation of orientation preference here. Both of them are present. So so the critical value of anisotropy for the creation of ocular dominance is it's not a species subject that has been interesting subjects in the mountain theory, because that depends on the type of these singularities of type of vortices, and it may depend on lattice and other things, but which can be computed in a way. So that's what we did. We did compute the critical anisotropy. So basically, what happens as a function of anisotropy is following. So the strength of ocular dominance in terms can be measured through so-called fluctuations in this G component of spin, so the edging part or ocular dominance part of the spin. So larger value of delta Sg corresponds to stronger ocular dominance segregation. So as lambda increases, the ocular dominance segregation becomes stronger. This special value of lambda is equal to 1 corresponds to so-called pure Heisenberg model, about which corresponds to Eigen-like model. So with ocular dominance maps showing more side patterns, below that, more intermediate value of anisotropy, then you get appearance of more blob-like structures. But if lambda is too small, you do not see the patterns. So this is numerical results, and we can also compute the quantities about the pineal densities in its time evolution. That is considered what is observed in experimentally, numerically, experimentally and numerically previous way. So this lambda, the answer between ocular orientation preference and ocular dominance columns is an important parameter of the problem. So basically what we have done is computed this critical anisotropy for creation of ocular dominance maps and try to construct so-called phase diagram in the parameter space of the synaptic interactions. Here, what we used is the synaptic, this inhibited in the space of, this is a cooperation range of cooperation of orientation preference map, this ocular dominance map. So in this parameter space, we are able to construct, say, a phase diagram for different states. In the context of magnetism, it can be called Ising, or this in-place voltage stable, or out-of-place voltage stable. There are 3 different regimes. And this can be mapped into our language of this cooperation of elliptic interactions. Then, in Ising regime, you must see a parallel band in ocular dominance maps, as you see here. In the case of this this intermediate region, you should see beaded bands. And down here, you should not see any ocular dominance maps. So this theoretical prediction can be checked for the experiment, because in the experiment, what you can find is wavelengths. So you can measure actually wavelengths of this orientation preference maps and ocular dominance maps. So the ratio of these wavelengths is related to this anisotropy of our problem. So you can actually measure this anisotropy for monkey in the case of cat and the feather, not in the case of tissue because there is no ocular dominance map. But this, experimental value is well in these regions. So basically, I mean, we think that ours is simple model with general symmetry and traction. It's capable of predicting existence of 3 distinct regions consistent with what has been experimentally observed. Unfortunately, these are all the data we have. I mean, we'd like to see more data to check the final details of our models. But anyway, I'm very happy with this result. Well, functional maps are abundant in brain. So we are talking about orientation preference maps and ocular dominance map. There are certainly more labs in the higher level of visual, primary visual cortex. But that is still have to be explored. And also in other regions of motor cortex, and somatosensory cortex, and other cortex, that different layers of maps are formed. So, well, I don't know how to proceed, but I'd like to be interested in pursuing these kind of questions in other problems as well. The second class of problem concerns this functional electrical formation in the brain. For example, in this experimental numerical study of functional MRIs by Nicholas et al., they studied these functional MRIs in say, so-called voxel images, the images. So it's three-dimensional images. So they measure this time evolution of these three-dimensional images with a spatial resolution, and then they compute the linear correlations between them. It has form a matrix, so-called correlation matrix. Under thresholding, then some thresholding, then they can create a thresholding matrix. So this defines some pruned connections between different so-called channels. So they are asking question of what will be the structure of this so-called functional or pruned network. This basically what they have observed is that this network they observed looks quite complex, but with some structures. So, for example, they say this is so-called small world, meaning it has a small average path length, from one subnode to another, but with a high clustering. Also, it has very, very defined so-called power law structures. So, in terms of number of nodes and its distribution of the different thresholding parameters, it shows the power law structures. It's called scale-free structures. But this is a highly, not just random network with very high structures. And also there has been studies of, trying to understand that the network properties of the brain, in terms of the elegance and in the monkeys, in the cat, cortex. So they sort of to indicate, even though they are small networks, indicate that these networks have certain structures which have the resemblance of this sort of small world complex scale-free networks. So this sort of provides a lot of motivation for studying this so-called neural network models interacting through this so-called SDP. But I think Dr. Sin is here. I don't have much, so you can go to this poster over there where Dr. Sin is going to explain in more detail. But what we are trying to understand is we have a network with this particular synaptic interactions. So depending on spiking timing between presynaptic and postsynaptic neurons, but it can weaken or strengthen, the synapses. So the synaptic plasticity, interacts, change activities. Also, activities change synaptic plasticity. So this is, interplay between this function and structure. So we are trying to understand how this interplay is going to affect the network structure of the nervous system. So one model is going to show is dynamic model of neural networks. So change plasticity induced by APCTP. And this neuron model is visual number neuron with nervous excitation. So some sort of equations, and we start the synaptic model, and then we start initially from the all-to-all coupling, the globally coupled network, and evolve the network under our evolution rule, and try to understand how that this functional network emerges through self-organization, which may have some insight into an active-dependent development and plasticity. So these are basically the core results of these experiments, which Dr. Sin is going to explain in more detail. Basically, what is observed in terms of node distributions, incoming and outgoing, you see a sparse network, because you start from the global network, but this self-evolution, the organization process, prunes some unnecessary synaptic connections. So with a certain threshold, it becomes sort of binomial distribution, and so it's active, so-called synapses form a sparse network with a small world character with some scale-free properties. Also, this is not a static network; it changes in time. So, because of the nature of the SDP,
the spiking time is highly sensitive, central process is highly sensitive to the timing, the temporal order of presynaptic and postsynaptic spikes. So it creates dynamics similar to what you find in the center part, so-called self-organized criticality. It creates avalanches, like in the center part model. So it forms in a kind of self-organized critical state with some balanced, say, excitatory and inhibitory connections. Then this network can be useful because it can show fast and high coherence, also fast and strong synchronies at the same time. So this can be in a way more dynamically more effective and structurally more robust. The third class of problem we are studying is trying to understand global functional pathways in electroencephalograms. So for this, we are cooperation with the Department of Anesthesiology of Hyundai Asan Hospital in Seoul. Basically, we want to understand the correlation between some feedback integration in the frontal posterior network with some source of conscious information processing in brain. In the case, anesthesia experiments with a human subject, which is informed in this center. So we are trying to do analysis of this network pathways based on information flow between different EEG channels. So basically, what you're trying to understand is how the primary information in the sensory system is transported to this frontal area, and how this information is processed back to the sensory system. So there's a hypothesis that the loss of consciousness is, in a way, is correlated to the breakdown of this pathway. So we are trying to measure information flow between these two pathways from the EEG channel data, and in time, so we are measuring, in fact, cross-dependence between these two channels. Basically, what we observe is that one of the pathway remains intact, this effect. The other pathway shows sharp decrease after administration of this resistant drugs. So this is something we've been working very closely with this group. Another, which is a little bit more wild, is that we are trying to understand the issue of the corneal space. Basically, we are trying, from the EEG channel studies, we are trying to find a cluster of channel patterns. So how many times these cluster patterns appear in some space, so in the space of the pattern. So we are construct a space of patterns, and we are trying to kind of correlate it with the notion of corneal space, and then try to construct kind of trajectory in this pattern space, and we are trying to understand what will be how this brain state is changed quantumly in this space. Basically, for this, we are measuring this correlation dimensions of this states in the space. This is a work in program, frequently written, but we are in the process of submitting now. So basically, the brain is a high frontier of complex systems, and we've been doing a series of studies in these directions. We are also doing the functional development of creation of asymmetry through the kind of symmetry breaking the problem, and how the area is differentiated. And we also try to understand so-called orientation tuning, sharp tuning of orientation preference through synchronization of the neurons in functional columns. And in a sense, the brain is a very nice paradigm for complex biology system, because I say this is highly nonlinear neuron and complex natural structure, and there's an interdisciplinary self-organization which leads to activity-dependent neuroplasticity. So this is very fertile ground for new quantum methods in the form of nonlinear dynamics, statistical mechanics, and computations. So we'd like to understand the role of biocomplexity in the nervous system and theory brain function. So this is work in progress and turning ahead. This in fact is widely noted by the physics community as one of the top 10 unsolved problems. Okay, thank you very much.
So thank you for a beautiful talk. And so, questions?
Depending on the species, you successfully modeled how input signals can create visual maps. I have several questions. I would like to know whether there is some time dependence or history dependence about visual maps. The second one is there any feedback mechanism from higher level of brain? You are saying about input signal causes visual maps, but I would like to know whether such visual map is completely stabilized or is it modified from higher or higher level brain? And the final question is how such visual maps are composed against external noise, such as electromagnetic field or thermal noise or something like that.
Okay. Well, thank you for the question. Those three questions are very important questions we would like to explore in the future. And for the first question, well, so can be history dependent. But in our model, it predicts robustness of patterns. So you can start with different random conditions, but it still creates similar maps. But so it's depending on the visual experience or environment when this kitten is exposed, that may change the maps, visual maps. So the visual environment and experience can be important. So if some experiments expose kitten in a cylinder, confined in a cylinder with only vertical stripes, so that affects this formation of the map strongly. So that's a very important question. And your second question is that, well, certainly this is not the end of the story. Certainly this map is also interacting with the maps of higher order. So how does it interact? That is not really well understood, because this kind of connections and the interactions, it's not really well understood. But basically what it did is kind of the first kind of study of classifying a typical pattern. So more detailed features of these patterns certainly should depend on the interaction with a higher level visual information processing and more. Your third question was
How
noise.
Yes.
Noise. Yeah, I think noise is going to play a role. But in our model, we expect reasonable noise is not essential in disrupting this pattern. So this is also feature under reasonable noise, because already our this brain is exposed to a lot of noise. So still we see creation of visual maps, a very robust creation of visual maps. So this is in fact the noise robust phenomenon, I believe. Thank you so much.
Related to this, how these difference between these three patterns, how these influence to the function of this visual. So depending on the three patterns, is there some difference in function?
Oh yeah. Well, that's very interesting question. In fact, I received those questions, but I do not have a clear answer. But there's a speculation. It's from some biologists saying, you see, monkeys have these eyes, more upfront eyes. Okay, cats will be sideways, and this fish will go this way. So the strength of ocular dominance somehow is related to to the kind of geometry of the two eyes. But is that, but is that the real answer? Even biologists I talked were not pretty sure. There was a speculation because if eyes are too much wide apart, then this ocular dominance becomes weaker. Yes. But I'm not sure whether that's the answer. Maybe some of the audience may provide better answers to these questions.
I wonder how many of the patterns that you show are dependent in detail on the model, on the mathematics of the model, and how many of them are features of short-range activation and long-range inhibition. Because many of the things you showed are similar to what people modeling developmental phenomena come up with, these so-called Turing-like patterns.
Yes, but this is in a way widespread phenomenon, the competition between stripes and blobs that can be seen in numerous, say, nonlinear complex systems, including chemical reactions. In this case, the most important fact is that this interaction function. So this short-range excitation and long-range inhibition. But the precise details of the form of this function is not important. It's not relevant to what you observe. In fact, what I think is that this kind of symmetry of this problem, that is XY-like kind of orientation symmetry, O1 symmetry, and this is a G2 symmetry of Eisenhower, so that's what the physicists like to say, or along with this particular, not particular, just general interaction, nature of general interaction. They are the only important factors which are capable of creating this kind of pattern. But in order to determine this kind of critical anisotropy, okay, which separates two different regimes, then precise value of this anisotropy depends on the details of interactions and the parameters. So one thing we are trying to stress with this study, and this is quite general prediction, which may be in a way consistent with what has been said in some cases with other neural development models. Right? But this is the kind of simplest explanations we can find without concerning too much detail about neural control. Because the answer is not clear if you move the reactions.
Thank you for very nice talk. I'm working on scale-free Boolean network. Just you. I'm very interested in the brain part. You show brain shows scale-free connection. Giving some example from sound piling, which is famous. But in sound piling, the phenomena is time dependent. Just you put the sound from the top, right? But then sound still keeps the same shape. But in brain is fixed once my brain is formed, right? It's never.
No.
No.
Answer is no. That's what I said from the beginning. Brain is plastic. It has plastic hardware. So this plastic hardware is driven by the so-called spike time independent plasticity, APCTP. So depending on the activities of two neurons connected by synapse, it can either strengthen this synapse or weaken this synapse. That happens all the time. So if you have learned something from this lecture, then your brain structure has changed already.
But isn't it a local phenomenon?
What?
But make a scale free, you must connect very globally.
Oh, I see. Well, from the beginning, I said brain is organized in different areas and in different hierarchical structures. So, for example, in the case of visual information, that's primarily processed in so-called visual area in the cortex on the back. But there, not just the one. numerous neurons or functional columns respond to the same stimuli. So it's already huge numbers. It's 100 billion neurons. No, 1 billion neurons. 100 billion neurons are already existing here. In this area, there's already many number of neurons in primary visual context area. So, but typically the kind of complex network study which shows scale-free property, you do not work with more than say 10,000 or 100,000. So that's a typical number. So there's already more numbers of neurons functional current involved in this process.
I see. Thank you very much.
Also, I stress because that's shape change occurring all the time. So our network is changing all the time with the shape structure, but dynamically it maintains this self-coherent critical state in the same way as this center part maintains this SOC state.
Okay, I'm Leif Salvo from Lund in Sweden. Thanks for an excellent lecture to start with. And I have 2 questions. First, why do we have an ocular dominance?
Evidence.
Why?
Evidence.
What is it good for?
I'm a physicist. Very good physicist. I asked the same question, but I was not getting the answer, surprisingly. So, because it's not, in a way, biologically, say, critical. Yes, because you can still, that may depend on the optimal performance of our visual information, must be, but there's no kind of clear proof that the formation of the ocular dominance map is critical to the optical performance of this visual processing.
Okay, thank
Yeah.
you. I don't know either. But
Maybe
sorry,
there's
someone,
better answers from. Yes.
anybody has an answer to that question?
Okay.
Oh, you have one.
Okay,
Excellent.
so thank you.
From what I've heard, this ocular dominance increases sharpness, contrastness of with which we perceive the visual information.
I see.
So if all these neurons were sort of homogeneously spread in the cortex, it would be sort of noise would kill lots of sort of weak signals. So weak signals are perceived much better with this, visual maps.
Yes, but is there experimental kind of evidence?
Oh yeah.
Oh,
There's one species of crab, I forgot, the horseshoe crab, and there's a way to mess up this ocular dominance columns, and then the way they perceive weak signals worsen.
Okay,
Okay, thank you very much. I have another question, and that is this. I'm quite keen on your experiments, the human situation, with the EEG, because it's been told that anesthesia really cannot be explained by the Hodgkin-Huxley's model, because it just doesn't work according to that principle. And it could be so solitones that are influenced by the things around us. And in this case, the anesthesiology might be so that it works by the solitone theory. You would have a chance possibly here to see differences between different anesthetics. You might have a chance to see the mechanisms and to explore this very, very interesting field according to what I understand. Have you thought of that?
Oh, actually, in fact, this study of EEG is not based on the Hodgkin-Huxley model. It's too far away to come from the bottom. So basically, what you do is kind of time series analysis, so correlation analysis through the, say, computation of cross dependence of these different channels, so from time series. So it's not based on neurons, but basically this is signal processing. So we do not exactly understand what is the fact the underlying neural, say, mechanism or precise neural mechanism which exhibit this breakdown of these pathways. No. So, but it's relation to solitones. I don't have. I'm sorry.
You might have a way to continue to look for that in the model. That might be a fantastic contribution.
Yes, actually, we are very much excited to see this result because the data is not easily available. Because that experiment is done through this so-called clinic center, and they have to do it for all with the patients. But if you ask for more experiments, I can do it.
Okay, thank you very much.
Thank you for really interesting talking. I'm Shimizu from Kyoto University. I'm interested in self-organization brain. You constructed the visual map with Heisenberg model, right? So could you explain the relation with Heisenberg model? It is physics equations and the physiological data and physiological causality.
Well, so you are talking about how do I interpret this model starting from the network of, say, so-called Hawking-Huxley type models. Well, that's difficult, but which I can try, because basically this functional column is in a way composed of more than, I think, more than 100 neurons. So they are connected through an integrated way. It's not just one type of cortical neurons. There is kind of interneurons, but there is kind of well-defined, well-studied network of neurons. So we have to construct this model, and we have to put in the interactions between different columns. There's long-range interactions for intracortical neurons. So actually, we are in a way doing this experiment. So trying to reconstruct what's happening here. Basically, what you see is this a set of neurons in the same column is showing the synchronous responses to a particular orientational stimuli. Okay, so you have a different set of neurons showing different different synchronous responses to different orientation stimuli. And they are in a way laterally connected by long-range connections. So you in a way simulate the dynamics of this so-called, this coupled, say, neural problems. Then you have to ask the same question as we do. But basically, I think that we are going to obtain the similar results, even though we are working on this coarse-grained picture of the functional column by representing it by a single phase angle variable. If we are coding these interactions in a way, right way, then I think it's going to create a similar result. But that certainly have to be tested. But this is the way people study in the case of so-called orientation tuning problems. They work with physiological neurons coupled to each other in a column. So the columns connected, they simulate this system in a massive way, trying to understand this collective dynamics of this whole network of columns. But that can be done in a way.
Thank you very much.
I'm Dr. Otsuka from Tokyo. I'm interested in the difference of the left side and right side brain function as a medical doctor. So, did you have some comment on it, especially this loss of the function? You have a beautiful model. So, do you have some idea on the difference of the right side and left side?
Well, there are certain differences in functionally for the left hemisphere part of the brain and the right hemisphere part. But I'm not sure of, in the case of a visual information processing in the primary visual cortex, because here, as far as I know, information is evenly divided and sent to two different parts of the hemisphere for similar type information processing on the elementary level of visual information processing.
Yeah, however, as regards the loss of consciousness, maybe the difference.
Not problem. Oh, yes. Yes. Oh, yes. But that we have not paid our attention yet to that part. We just noted the sharp change in this across the bandits for the entire brain, not the different hemispheres. Yes, that's interesting suggestion. Thank you.
Questions? Okay, so if not, so it's for the time. So, okay, thank you again.